A primary challenge with natural language understanding is dealing with ambiguity. That is, a word, phrase, or sentence can have multiple meanings. Ambiguity arises in many forms and requires disambiguation techniques to handle. We can review the ambiguity problem in terms of the different levels of language analysis. Lexical ambiguities arise when we have words with more than one meaning. For example, you can have words with the same spelling that have different meanings, words that sound the same and have different spellings and have different meanings. And proper nouns can sometimes also be common nouns. In semantic scope, we can have ambiguities arise when sentences have more than one meaning. For example, when it's not clear who the subject is. In the example sentence, I can see the man with glasses. It's not entirely clear if the man is wearing glasses or I can see the man when I am wearing glasses. Plurality also results in ambiguities. They only ate the pizza. Did they only eat a single pizza, or did each of them only eat a different pizza? And ambiguities in the semantic scope can arise in terms of the preposition. There's a dog with a frog on a log. Is the dog with the frog and they're both on the log, or is the dog with the frog and it's just the frog that's on the log? So these all are examples of semantic scope ambiguities that can arise in language. There are contextual ambiguities, such as sarcasm, hyperbole, metaphors, implied meanings, and then cultural nuances and dialects. So a lot of phrases that we tend to use in language and have learned that the implied meaning is a certain thing when the phrase itself does not specifically mean what we are implying. Language is also evolving, which leads to ambiguities. Slang has changed a lot over time. Internet slang has added new words to the language. We have added emoticons and emojis to our text. And technology growth also adds new words to the language. As new technologies arise, we have new words that come along with them. There is ambiguity when there are errors in the text, such as misspellings or typos, or a wrong word choice has been made. The famous there and there, very commonly misused word choice in the English language. And when text has poor grammar in general. If you're directly following the grammar rules, there can be some ambiguity when the grammar of the text is poor. Of course, this is not an exhaustive list, but it does demonstrate areas where some ambiguities can arise. The next question is then, how do we handle disambiguation? According to Gemini, word sense disambiguation is a crucial task in NLP as it helps determine the intended meaning of a word with multiple senses in a given context. Choosing the right method depends on various factors like the availability of labeled data, computational resources, and the desired level of accuracy and interpretability. Often, a combination of approaches can be used to achieve the best results. In an example problem, the word bank can have multiple meanings. It can be a financial institution, or bank can refer to the edge of a river. And a problem might be to determine the correct meaning in a sentence like, I went to the bank to deposit money. Trying to determine in what sense we mean bank in this sentence. Let's look at an overview of some techniques broken down by their method category. There are dictionary and knowledge-based methods. These methods rely on external resources like dictionaries and lexical knowledge bases. The LESC algorithm is a classic example, and we'll look at some code for that in a minute, where the sense of a word is chosen based on the overlap between its definition and the definitions of the surrounding words in the sentence based on their available definitions in a dictionary. And of course, each word might have multiple definitions available in a dictionary. While this is simple and efficient, these methods might not capture all of the nuances of language, and they may be limited by the quality and coverage of the external resources that we have available to us to perform this algorithm. Supervised methods leverage machine learning algorithms. These are trained on pre-annotated corpora, where each word has its sense pre-labeled. We can use things like support vector machines and memory-based learning. These are popular choices due to their ability to handle the high-dimensional feature spaces. However, these methods do require labeled data. In most cases, quite a lot of labeled data, which can be expensive and time-consuming to either collect or create. We talk about supervised methods when we talk about natural language processing classification techniques. In classification techniques, we looked at a lot of supervised machine learning algorithms, like support vector machines, and reviewed some different techniques. So there's more detail here that you can look at for classification and machine learning, and supervised learning with scikit-learn, which is Python's library for machine learning. In addition to supervised methods, we have unsupervised methods. While supervised methods required labeled data, which as we said can be expensive and time-consuming to collect or create, unsupervised methods do not rely on pre-labeled data, and they try to identify word senses based on the context itself. Clustering techniques fall into this category. They can be used to group words based on their co-occurrence patterns, suggesting that the words have similar meanings. While these unsupervised methods can be appealing because they don't require the pre-labeled training data, they might struggle with things like ambiguities and may not always achieve the best accuracy for word sense disambiguation. Embedding methods is a growing area that utilizes word embeddings. These are dense vector representations of words that capture semantic relationships, so relationships in meaning. The idea being that words with similar meanings will have similar vector representations in this higher dimensional space of word embeddings. These methods can be powerful, but they often rely on pre-trained word embeddings, and they might not be easily interpretable. If you want to learn more about word embeddings, follow the Learn More link, and you will find a page on word embeddings, which is a common concept in deep learning for natural language processing. Let's look at some simplified coding examples for some of these methods. While this list of methods is certainly not comprehensive, we have covered the categories of types of methods, and many of which are going to be more in-depth in terms of implementation. But we'll look at a couple simple examples from the first two categories. The first one is a dictionary-based, using the LESK algorithm. And this simple code is trying to disambiguate bank in our example of I went to the bank to deposit money. So the sentence is I went to the bank to deposit money, and the word that we want to disambiguate is bank. And we will get the sense from an implementation of the LESK algorithm. So we're calling the LESK function, and we're sending it our sentence and our word. It is returning a word sense that we're then printing out. So what does our function look like? Our function is an implementation of the LESK algorithm. We are going to use NLTK, which is Python's natural language toolkit. And from the NLTK corpus, we're going to import WordNet, which will give us some predefined word senses. This will be our dictionary. So we start by getting sense sets for our particular word. In our case, our word is bank. And then we're going to store those in word senses. So word senses will now be a list of the senses of the word bank. We're going to iterate through the word senses, and for each one of them, we are going to get the definition for that word sense. And then we want to compute what I'm calling the overlap. So the overlap is going to be the length of our sentence split into words, taking the set of that, so it's the set of words in our sentence, and the sense definition that we just pulled from WordNet SenseSets. We're going to split that definition. Again, we'll have a list of words, and we can take that set to get the unique words. Now we have two sets. The set of words, unique words in our sentence, and the set of unique words in that definition. And we're going to take the intersection of those two sets, so we're using Python's set intersect. And then we're computing the length of that intersection. So that gives us the length of the overlap between those two sets. If the overlap is greater than our max overlap, which up here we have initialized to 0, then we're going to set our max overlap to this overlap, and we are going to set the best sense found so far to this word sense. And up here we see best sense was also initialized to none. So we're going through each of the word senses for the word bank, and we are checking the overlap of the full sentence, so it's taking into account the context of how we're using the word bank by looking at all of the words in the sentence around bank, and simply checking to see how many words overlap in that set of words versus the set of words in each one of the definitions. And then we're going to say that the definition that had the greatest overlap is the best sense, and ultimately return that as the best sense for the word. And you can copy this code and run it, and you will see that the output is a senset bank N07. So it's the 7th definition, and if you look up NLTK WordNet, and you can see the definitions of all of the sensets, and the definition for Bank 07 is a financial institution, which is accurate in our sentence, the context of our sentence. So it's a very simple, the LESK algorithm, it's a very simple algorithm, it's easy to implement, and we can readily do this with our NLTK library. But you can imagine that this is really doing a trivial cursory check of just the greatest overlap between the definition and the way that we are using the word in the sentence. Of course, that is going to be prone to failure in many cases, but it's also a good chance that this will often return the correct sense, given that the sentence that we're inputting does have a substantial amount of words around it, such that the sense of the word can be derived immediately from the context in which it is used. We'll look at another example, and this one is going to use supervised machine learning, and in this case we'll use the naive Bayes algorithm. Now, because we don't have a large set of training data, remember that supervised algorithms require a set of pre-labeled training data to train a model, to do, in this case, a classification. We'll make up some simple data for a trivial example of pre-labeled data that we can use to train the model to determine a sentence that includes the word bank and determine its word sense from the context. So in this very trivial example, we have 3 labeled pairs of data. In the first half of the pair, we have a sentence, and in the second half of the pair, we have the label. And in this case, the label is the word sense that applies to that sentence. So the first sentence is, I went to the bank to deposit money. And now we're using this as training data. And the label for that sense of bank is financial institution. And we provide another sentence. The river bank is beautiful. And we label that sentence with the sense river edge. So here, bank means river edge. And then the third sentence, the bank loan was approved, gets labeled with financial institution. So that forms our very trivial labeled training data. If you have done any prompting or prompt engineering with large language models, this might be reminiscent of few-shot prompting, where you teach a large language model a task using some minimal example. This might look like that to you if you've worked in that area. And from there, we are going to store data in a data frame, so our training data. And we are going to pre-process the data, where X is our sentences, and Y is our labels, and that would be the sense. So the input data and its labels. And we'll use a vectorizer to transform the data and fit it to a vector, which makes it amenable to machine learning. We'll split the data into training and testing sets, and of course our data set is incredibly tiny, so that is going to be a very minimal split for training and testing. We have a test size of 0.2, and we'll start with the common random state 42. Next, we create and train our classifier. So we set up our classifier. We're using the multinomial naive Bayes, and that is coming from scikit-learn. So we've imported all of these tools from scikit-learn, where we can do machine learning in Python. We create and train our classifier. So we create the classifier here, and then we call the fit method on that classifier with our training data and our training labels. And we call fit, which trains the model based on that input training data. Now, CLF, our classifier, is a trained model, albeit very minimally trained on a tiny subset of data. But we can see if, with that, the model is able to predict the sense for a new sentence. So the new sentence we'll provide is, I need to go to the bank to withdraw cash. We can vectorize this new sentence using the scikit-learn vectorizer and transform the sentence into a form that can be fed into the machine model for inference. And then we call the predict method to get the prediction of that new sentence vector and store that in the predicted sense, which we can then print out. And when we run this, we see that it prints a financial institution, so correctly choosing the class. So that is a very trivial examples. In fact, both of those examples were quite trivial, but that's just to get you started. Some improvements on all of the methods mentioned on this page include combining multiple techniques for better accuracy. So you can take the outputs of multiple techniques ran simultaneously and then do things like choose the word sense that the majority of the techniques returned. You can explore advanced techniques like supervised learning, using deep neural networks, so deep learning. And here I found a survey paper on lexical ambiguity detection and word sense disambiguation that was recently published. And I put a link to it here. This is a survey on lexical ambiguity detection and word sense disambiguation. So the paper is exploring techniques that focus on understanding and resolving ambiguity in language within the field of natural language processing, highlighting the complexity. This paper is available for download as of this recording. You can access the paper and view the full PDF to read this paper to continue your understanding of the current state of word sense disambiguation. The challenge of disambiguation in natural language processing is a difficult one, and there is still a lot of work left to do.